Hi, today I'm going to share with you some new graphs about the time dilation and also time contraction in special relativity. We started from Lorentz transformation for time. Transformation. According to Lorentz transformation, T prime, the time measured by the observer in the flying frame, can be predicted based on gamma factor and the local time in the fixed frame minus v divided by c squared times x. This is a famous Lorentz transformation. Now, if I rewrite this formula slightly, so what we can do is that we just put them as a minus bx. So what is a? So we have introduced a substitute variable here. So a will equal to gamma times t, and b will equal to v over c squared. Now for a fixed t, if the t is constant, the t is constant, t is a fixed constant. So this would be very simply a linear equation, right? So where we can draw a graph. So this we can draw the graph of this function. So if I draw, let me draw this is our vertical axis. This is a horizontal axis. In this diagram, I'm going to show you something very interesting. And the vertical axis, I will represent the t prime, which is the time measured in the moving frame with velocity relative to the fixed frame. While the horizontal axis will be x, will be the coordinate used by the observer in the fixed frame. Now this is origin. Now if we just plot this diagram, so we from here we can see that this is just the straight line with negative gradients. So can we just simply draw this draw a straight line here? That will give you the something like that, something like okay. And so of course this is we use arbitrary number for a and b, but once is a and b are given, and we should be able to denote the intersection or intercept. In this case, we can say, for example, oops, we still prefer to use origin color. So this straight line. Let's make this straight line first, and then we move to they change the color to this one. Yeah. So obviously, according to our high school knowledge, is that this will be the y-intercept. So this is this x equal to 0. This will be the a. There will be the a, and this one will be our x-intercept. Okay, in this case, x-intercept would be a positive number. Would be a over b. Well, it looks simple, right? We're going to discuss that. Obviously, when the x, you see, that's something very interesting. So that is the dependence of the t prime on the coordinate x. Okay, we pick up two different variable from two frames of reference. Now, obviously, that the t prime will be positive as long as x is smaller than a over b. However, so this is where the t, this is where what would happen here, that the t prime will equal to 0. Well, in this, on the other hand, over that side, if as long as the x is large enough, then that t prime will always a negative number. So in principle, what does that imply? That you can actually trace back the history of the early history by just move the position as far enough from the origin, then you should be able to see the past of what had happened in the flying frame. That would be interesting. So that is one implication. another thing is I'm going to fix that is if we fix, because since the t is a fixed constant, so therefore we should be able to simply draw a straight line to represent this particular constant. In this case, as I said, the t is fixed. So if I just draw a straight line, it's arbitrary straight line. Oh, sorry, I have to probably. So if we draw a straight line to represent this constant t, that t prime t, remember, is our t, then something interesting happens. We know that this is there is another intersection come, So that actually the intersection here, you can see, perhaps you have noticed that there will be another intersection here, okay? Now using the simple mathematics, high school mathematics, we should be able to pinpoint this particular x. So the x will be equal to the t, with t is fixed, that will be equal to a plus t divided by b. Okay, I give you some time. You can figure out this simple relation, simple formula for this turning point, or cross, rather I call it, it's a turning point. I'm going to say that. So what does that mean? Can we enable that? Can we enable this curve before we go further? So the green line will be represented t, and the orange one will be represented t prime. So what happens that at a particular moment in the coordinate of x, there exists a particular position in x of the fixed frame where the t prime equal to t. Bear in mind, in this case, the frame is moving as fast at a certain speed. So basically, bear in mind what I'm talking about here is that we are still talking about this scenario. Oops. So let's draw the two frames of reference of this scenario. Okay, that is horizontal axis. There is a moving frame here. You can imagine that the frame is moving. So, so this will be our S frame. This will be our S prime frame. And there will be X prime. This is X. In this particular diagram, we are only pick up X and T prime. So bear in mind that the frame is moving at a constant velocity. That would be the V positive. So that is velocity. So this is our zero, this is 0 prime. So we've got 2 clock, we've got 1 clock here. Let's draw a clock properly. Yes, we should be draw the proper circle. These are 1 clock. There's another clock here. So there are 2 clock here. So we have 2 clock here. So one clock read is a t, another clock read is a t prime. So this is can we just draw the simple, But the convention is that many people believe that the moving clock many people would accept that the claim. Many people would accept the claim that the moving clock will go slower. So they just follow the consensus for the time being. And of course, so this would be the diagram of the real motion. Okay, this frame could be fixed in a spaceship for the non-distant travel. Now that's something very interesting happens that you will notice that in this region, t prime is always smaller than t. Okay, as now as x is over this intersection. On the other hand, the t prime is always larger than t. So there are two scenarios here. For people who get so used to the formula for time dilation, this is what you expected. So t will, in this case, T is in this case is a time dilation. So in this case, the time actually is a time dilation. Time dilation. So the moving clock is always slower. However, if you look at this relation, then that will imply the time contraction. Time contraction. That is the main point of this short video, that both time dilation and time contraction can occur. Okay, those who claim that the time variation is always based on this formula. This is formula is popular formula is that delta t or t, delta t will always equal to delta t prime divided by this square root 1 minus v squared divided by c squared. Okay, so this formula, although has been used by many people, this particular formula I have to highlight as well. So this is what we call the time dilation formula, in which that the time measured in the fixed frame is always longer than the time measured in the flying frame. So hence people claim that, look, the flying clock getting slower. But based on today's discussion, it is certain that not only can time dilation happen, as long as the x, the position of the object measured in the fixed frame is large enough. You will actually substitute the number to see for the given velocity and what would be this particular x-intercept. Okay, it's a huge number. I can tell you it's a huge number. So now as the position is large, then time dilation occur. Otherwise, if x is less than this x-intercept here, and or even become negative, so everywhere you will see time contraction. What does it mean, time contraction? So in fact, the clock of the moving clock is actually run faster than the clock stayed in the frame S. So that is the simple graphical discussion of the logical consequence of the Lorentz transformation. So from now on, be careful. This formula is only true when certain conditions are applied.